Let's look at problem 3 from exam number 1, summer of 2007, and try to analyze it. This problem wants us to write the node voltage equations for the given circuit and place those in standard form. For node voltage equations, what we need to do is start identifying nodes. Right now it looks like this would be my bottom or reference node that I would select. Then this looks to be a node that I would like to define. Here's another node, let me call it 2, and now I have a third node between R sub 3 and this dependent voltage source, and I'll call that node 3. What I now need to do is create or write equations associated with each of those nodes. I now am saying that I have 3 unknowns. I have this unknown V sub 1, voltage drop from node 1 to the reference node. I have V sub 3, the node voltage or the voltage drop from node 3 to the reference, and I also have V sub 2, which is the voltage drop between node 2 and the reference node. I've now defined my node voltages. I need to write my equations, and for node voltage analysis we're writing Kirchhoff's current laws for the algebraic sum of the currents at each node. And typically I will write all the currents leaving the node, although if I have a current source sometimes that will be on the other side, or depending on whether it's coming into or out of the node, I may just leave it as it is. Let's now start writing KCL for node 1. We have I sub 1 already identified for us. We'll just leave that as I sub 1. We also have this current, let's call that I sub 2, and let's call this current I sub 3, and we have the current going up, which in actuality is exactly the same as that source voltage, or I'm sorry, source current 6 amps going to the right. Let's now write the KCL equation at node 1. Current coming down, first one on the left is going to be our V sub 1 over 1, or R1, plus then the second vertically down current is V sub 1 over R sub 2. The current going from left to right through R sub 3 is then V1 minus V sub 3. That's the voltage dropped from left to right across R sub 3 divided by R sub 3. And the other current going vertically up is also leaving the node, and that one is, like we said before, actually equal to that source current that's going to the right, and that's 6. That's equal to 0. We can combine common terms, and we now have 1 over R1. Let's go ahead and replace that with its numerical value of 1. 1 over R sub 2, which is 1 over 2, and 1 over R sub 3, and R sub 3 is 3. Those all multiply V1. We have nothing multiplying V sub 2. We have 1 over R sub 3 multiplying V sub 3, or we have minus 1/3 V sub 3, moving the source term or the other terms that are not multiplied by any of our node voltages on the right hand side says that we can do that by subtracting 6 from both sides, or adding 0 to the equation, which gives us now minus 6 on the right-hand side. This is now one of our 3 equations that we need to find. We now want to write KCL at node 2, and in doing that we'll be looking at trying to find then this current, which is given to us. We have this current, which will be V sub 2 divided by R sub 4. We have this current, which is actually just the negative of that 6 amp source. And finally we have this current going from right to left through that particular dependent source. And that particular current is not what we want. Well, it is what we want, but we do not know what the current through that particular dependent voltage source is, and because of that, let's then say, you know what, we can't write KCL directly at that particular node 2. We actually have to do a supernode and enclose that dependent source inside the supernode and write KCL relative to that supernode, which really means that now instead of this current, we just move it over a little bit and we want to know that particular current. Let me go ahead and label this. Let me say that's I sub 2 source. Let's call this I sub 1 source. It's actually the negative of that 6 amp. Let's call this I sub 4, and this current let's call I sub 5. Meaning the sum of those currents leaving the supernode, we had to do the supernode because we could not find the resistance of that dependent source. We can determine the voltage drop across that. It's just depending on which direction we want it to be defined in, but we could say V2 minus V3 would be a positive drop from right to left across that dependent source. But we'll come back to that in a little bit. Because of this supernode, we'll have to do something other than a particular another node voltage equation. So if we write KCL at the supernode, remembering my currents that I had defined, I now have the sum of all of those currents needing to be equal to 0. Or I now have I sub 5 plus I sub 4 plus I sub 2s plus I sub 1s equaling 0. And I'll try to write those down then. I have I sub 5 plus I sub 4 plus I sub 2s plus I sub 4s, I sub 1s and I sub 1s then is equal to 0. To find those, I sub 5 is just the current going from right to left through R sub 3. That's V sub 3 minus V sub 1 over R sub 3. I sub 4 was the current going down through resistor R sub 4. That's V sub 2 divided by R sub 4. Then we have I sub 2 source, or I sub 2s, leaving, that was 2. And then we have I sub 1s, which the way I had defined it is in the opposite direction of the 6 amp source, so that's now minus 6 equaling 0. We can now collect all of those terms, and the ones multiplying V1, we have a minus 1 over R sub 3. R sub 3 is 3, that's V1. The terms multiplying V sub 2 are just 1 over R sub 4, and that will then be plus 1 over 4 V sub 2. Then we have one coefficient for V sub 3, which is 1 over R sub 3, or 1 over 3 V sub 3. We combine 2 and minus 6 to obtain minus 4. If we add 4 to both sides, we'll end up with the node voltage equation or values on the left equaling something that's forcing those on the right, and that something in this case is actually 4. That's now our second equation that we need to write, and we need 3 because we have these 3 node voltages that we have created or defined, V sub 1, V sub 2, and V sub 3. If we go back to our circuit, we'll see that we are not going to be able to write another KCL expression at node 3 because, again, we do not know the current going through that dependent source. For that reason, we have to come up with another equation, maybe called a constraint equation, that will define or relate the different node voltages, V1, V2, and V3, to give us a third equation, a third independent equation, independent of the ones we've already found. We found one collection of equations at node 1. We found another collection of equations due to the supernode. Now what we need to do is find another third independent equation. The first two were found with KCL. Now maybe what we need to do is write a KVL equation, and we can do that actually here. If we just go up, we can go across an air gap. That's completely valid. And we can write a KVL equation from here over through the dependent source and then down through V sub 2 and across. Meaning writing KVL because of the, or near the supernode, so let's say KVL near the supernode, allows us to then say we have minus V sub 3. We're going into the minus terminal before we hit the positive terminal on V sub 3, plus 5 I sub 1 plus V sub 2 is equal to 0. That would be our third equation. Well, it is our third equation, except we really don't want this fourth variable. We just want 3 variables, unknowns, and now we've introduced a fourth unknown variable, I sub 1. We need to get rid of or eliminate this I sub 1, or rewrite I sub 1 in terms of our node voltages and sources, V1, V2, V3, and sources. If we look back at our circuit, I think you'll find that on the left-hand side we had a resistor, R sub 1, and that resistor actually was where I sub 1 was defined. It was the current through that resistor, and we defined this voltage drop to be V sub 1. That now allows us to relate I sub 1 via Ohm's law to the node voltages, and in particular we know that I1 is simply V sub 1 over R sub 1. that allows us now to replace I sub 1 in this equation. R1 is just 1. This is now V sub 1 over 1, or V1. Now we have our third equation that we need to solve the problem. We now have 5 times I1, which is I1 we just determined was V1. We then have minus, well, let's go in numerical order. Let's say plus V sub 2 minus V sub 3 is equal to 0. And that's now our third equation that we needed. We needed 3 independent equations for this particular problem, and I've now boxed those, and that really actually, the way that I had boxed those are in standard form. You could put that into a matrix if you wanted to. We haven't talked about that so much in this class, but hopefully you're starting to get comfortable with writing these in standard form, and that should fairly easily translate into a matrix. But in this case we have a common denominator, we could say, of 6 on the coefficient for V1. We then have 6 plus 3 plus 2, or 11 over 6 times V1 minus 1 over 3 V sub 3 is equal to minus 6. There's our first of the 3 equations if we want to write those now in standard form. We would have 11 over 6 V1 plus 0 V sub 2 minus 1 over 3 V sub 3 is equal to minus 6. Our second equation came from writing KCL at the supernode, and that now has a minus 1/3 V1 plus 1/4 V2 plus 1/3 V sub 3 equaling 4. We can just rewrite or copy that down, so we now have minus 1/3 V1 plus 1/4 V sub 2 plus 1/3 V sub 3 is equal to 4, and our final equation that we need for writing this in standard form is then the last one that we just wrote that was in black, and that's 5V1 plus 1V2 minus 1V3 equaling 0. And that's now our equations in standard form. You can write that in a matrix if you wanted to. That's not necessarily required. This is good enough for standard form. But if you wanted to, that's now 11 over 6, 0 and minus 1/3 times the unknown voltages, V1, V2, and V3. And on the right-hand side, we have minus 6. What we can do then, once we've put it into a matrix form, is we can invert this matrix on the left and solve for V1, V2, and V3. Meaning the solution is now immediately available to us if we can invert that matrix. And a lot of calculators will do that. There's a lot of numerical analysis software that you can use to allow that to happen. And there would be our solution, although I did not ask for that, or that was not asked for in this particular problem.